So I was discussing about elastic potential energy and gravitational potential energy. Suppose if you are holding a stone or something above the ground, it can do some work. Okay, so that is said to be gravitational potential energy. Elastic potential energy means, so have you seen Bahubali? Yes or no?
Yes, sir.
Yeah, you have seen, right?
Yes, sir.
So there is a bow and arrow, right? So when you the bow and arrow is there, and there is a cord, the arrow is fixed. The tail of the arrow is fixed under the cord. Okay. So, but I couldn't understand until now how he could put 4 arrows in one cord, right? 4 or 3? I don't know. But really, it's amazing. At 4 arrows, I think he puts in one bow. Okay. So, but when you stretch the cord, the energy stored in the cord goes to the arrow. Got it? The energy stored in the cord goes to the arrow. So here, what is K here? K is spring constant or elastic constant. K is spring constant or also known as elastic constant. Elastic constant. And what is X? X is the displacement. K is the elastic constant and X is the displacement. Is that clear?
Yes, sir.
Yeah. Please do copy this. We will go to the. Can I erase this one? Here.
Yes, sir. Half where?
Yeah, this one. Can I erase this? Now, what is kinetic energy then? What is kinetic energy?
So in elastic potential energy, why have we taken half there?
Why you are taking half? We will derive
Yes,
this.
sir.
We will derive this. Okay. There is a derivation for elastic potential energy. You know that MGH is very simple to understand. How did we get that? Force into displacement. So the force is mg and displacement is h. Multiply, you got mgh. When we come to this, I will derive it now. Okay. And we have kinetic energy. So what is kinetic energy? Kinetic energy is energy possessed by the body. Energy possessed by the body due to motion. Due to motion. So what is the formula? Kinetic energy equal to half mv square. How did we get half mv square? Any idea? This we have done in grade 9. You have to go back to the equation of motion. You have to go back to the equation of motion. V square minus u square equal to 2as. Okay. MAS will come, no? See, we have the formula V square minus u square equal to 2as. So, if u equal to 0, implies V square equal to 2as. So, we need as. As equal to how much? V square by 2. Actually, work done is equal to force into displacement. So, implies W equal to MAS, MA into D. So, or MAS we can take. Okay, you can take S also, not a problem. So, AS is what? W equal to M into AS is V square by 2. So, that is the reason we are getting half mv square. Got it? So, kinetic energy equal to half mv square. Once again, see, we have the formula V square minus U square equal to 2as. If the body is moving with a uniform velocity, initial velocity is 0, you got V square equal to 2as. Cross multiply, AS equal to V square by 2. Work done is equal to force into displacement. Work done is equal to MS. M into V square by 2, we get half mv square. So that is how we got half mv square. Now here, we will do work done by variable force. Okay, work done by a variable force and work done theorem for a variable force. Both we have to do. Constant force and variable force. Is it clear, girls?
Yes, sir.
Please do ask if you don't understand at any point of time. Now, going ahead. Now, so work done by a variable force. Until now, it is constant force. We are applying a constant. Now, we are going to apply work done by a variable force. Work done by a variable force. So what is that? So we have delta W equal to f of x into delta x. If there is a, let's suppose example, a bus broke down and around 4 people were pushing the, or maybe a car broke down and 3 people are pushing the car. Maybe after 1 meter, one more looking at these people, one more car that also came and pushed he also came and he also added with these 3 people. Now how many people are there? How many people are pushing the car now? 3 were there before, 1 added now. How much?
4.
4.
4.
Now what happened? Suddenly, 2 people were called after 1 meter. Again, two people were called for doing some work. Then 2 of them, they left the car, pushing the car. They left pushing the car. Now how many are there? Yeah. How many are there now?
2 are there.
2 are there. 2 are left. In the beginning 3, then 4, then 2. So do you think the force applied on the car was same throughout?
No, sir.
This is
No,
very
sir.
important because the concept what I am teaching now is very important for grade 12 in electrostatics lesson. Second chapter, electrostatic lesson, electric potential lesson. You will be using this concept again. So there you should not be blank. So second lesson, first part, electric potential chapter part. So so what is this here? Force is not uniform. It is not constant throughout the displacement. First meter, 3 people were there. Second 1 meter, 4 people were there. Third meter, only 2 people were there. So the force applied on the car was not the same throughout the motion. So that is why we have taken the piecewise. Piecewise means what? A small displacement, small work done. First part, second part, third part, like that. So we have to calculate the total work done. I have to add all of them. W equal to summation. We say sigma, right? Summation xi to what? Xi to xf, f of x into delta x. Understood? Xi to xf, f of x into delta x. Now suppose, example, we have, what is this? This is said to be summation. It's a sigma, right? Summation. Summation means sum of all terms. Sum of all terms. And this is said to be integration. This is used when we have discrete values. We have discrete values, we use summation. Like in statistics, we were using this. In grade 10 statistics, we were using summation. Now next part is what? Integration. Integration we use when we have continuous values. When we have continuous values. Sigma used for at the time of sum, that is for discrete, and integration is used for continuous values. So xi to xf. Now xi is initial position. Xi is initial position. And xf is what? Xf is final position. Xi is initial position, xf is the final position. So what is that? W equal to what? W equal to limit delta x tends to 0. Summation xi to xf. Summation xi to xf. F of x into delta x. Why we have taken delta x tends to 0? Because the value is very close to 0. Understood? Let's suppose we have the work. This is work done. So this is what the area under. One more thing. The area under the force distance graph or force displacement graph gives work done. The area under distance, the force and distance or force and displacement graph gives work done. I'll write here. The area under F and D gives work done. F and D gives work done. Now see here. See this is F and D. What we are doing now? This is piecewise. We are dividing this area into so many pieces and calculating the area of each and every piece. Maybe the first one is a trapezium, second one is a trapezium, third one is a rectangle, like that. We are calculating the area of each and every piece. This is again used in mathematics in integration, grade 12. Okay, and there we will be using again this thing. So area under F and D gives work done. So summation is used for discrete values. Integration is used for continuous values. Xi is initial position, xf is the final position. Now what I have done here? Summation xi to xf, f of x into delta x means what? How do we write this? F1, f of that is f into f1 into x1 plus f2 into x2 plus dash 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 fn xn. Okay, like that we keep on going. Okay, so that is how we write. So instead of writing like that, we are writing summation xi to xf, f of x into delta x. But I wrote here delta x tends to 0. Means what? The value of x is very, very close to 0. Very, very close to 0. The more you go close to 0, the accurate value you get. Like we have done in the variable, what is that? Variable velocity. Or variable velocity or instantaneous velocity concept. There also we have taken delta x tends to 0 or delta t tends to 0. The more you go closer, the more x will become small, the more accurate will be the value of the work done. So limit delta x tends to 0, summation xi to xf, f of x into delta x. Is it clear? Is it clear, girls?
Yes, sir.
So this is the concept of a variable work done by variable force. Work energy theorem for a variable force. Work energy theorem. Work energy theorem for a variable force. Work energy theorem for a variable force. So we have see the formula for kinetic energy is half mv square. Formula for kinetic energy is half mv square. So dk by dt equal to what? D by dt of half mv square. D by dt of half mv square. So what we are going to do now? We are going to take m common outside, 1 by 2 and m. So we are taking 1 by 2 m outside, d by dt of v square. So d by dt of v square. So v square can be written as v into v, half m dv by dt into v. dv by dt into v. Okay, so dv by dt into v. Now we can write 2v into, we can write otherwise, we'll differentiate it here. V square derivative is 2v into dv by dt. Derivative of v square is 2v into dv by dt. So this and this will go away. So this velocity is left over there. So m into velocity can be written as dx by dt. dv by dt is written as a. Okay. Rate of change of velocity is acceleration. Velocity can be written as rate of change of displacement. So already we did it before. Okay, acceleration here, velocity equal to dx by dt and acceleration equal to dv by dt. This we did in second chapter or second chapter, motion in a straight line. So the same way we did here. So ma is what? Dk by dt equal to what? Ma is force. Force into dx by dt. Force into dx by dt. Now dk equal to what? dk equal to f into dx. dk equal to f into dx. Now we are applying integration on both the sides. dk is equal to integration f into dx. From where to where? Initial to final. Here also initial to xi to xi. Initial to final. Now when you integrate, see integration of dx is x. Integration of dx is x. Now suppose if I write xi to xf, like a to b, example, this is a to b. A to b is the limit. How do we write? A to b. Then upper limit minus lower limit. This is the way we do the integration. Integration a to b f dx is what? Dx integration is x. This we have done again in second lesson. So a to b upper limit minus lower limit. So we integrated to find out the entire value. Now dk equal to what? Dk equal to k from where to where? Initial to final, ki to kf, which is equal to f into, and f is constant, take it outside. Dx is again x, xi to xf, xi to xf. So how do we write now? We write here upper limit minus lower limit, which is equal to what? F into upper limit minus lower limit. Upper limit minus lower limit. So we write here kf minus ki is equal to f into x. So that can be written as work done. Change in kinetic energy equal to work done. This is again work done theorem for a variable force. Once again from the beginning.
So after that integrate like d by dt of v square, how did you get dv by dt?
Yeah, I'm doing here.
Half m into 2v and then dv by
From the
dt.
beginning. From the beginning, see half kinetic energy is half mv square. Derivate differentiate on either of the sides. Dk by dt equal to d by dt of half mv square. Now what I have done, half m I have taken outside. D by dt of v square. Derivative of v square is derivative of
2v.
v square is 2x. Derivative of v square is 2v. 2v
Yes.
into dv by dt.
How did you get the dv by dt?
Yeah, this is, see, if it is x square dx, then we can write 2x. Directly we can write 2x. But the problem is,
Oh, so here it's t and then it's v. So
t.
then we have multiplied divide.
That is the reason we are not able to write like that. So we are writing dv by dt. So half m into 2v into dv by dt. M into what is velocity? Rate of change of displacement. dv by dt is acceleration. So velocity is equal to dx by dt. Acceleration is equal to dv by dt. So dk by dt equal to what? M into a force dx by dt. Now dk is equal to f dx. Apply integration of both the sides. Ki to kf, xi to xf. So here integration a to b dx is equal to x from a to b, b dot, b minus a, upper limit minus lower limit. Same way, ki to kf, f into xi to xf. So what? Kf minus ki is equal to f into xf minus xi. That is equal to f into x. So kf minus ki is equal to work done. Understood now? Is it clear?
Yes, sir.
Yeah, please do. Concept of potential energy. Concept of potential energy. We write here f of x is equal to what? F of x equal to minus dv by dx. Means if we differentiate the energy, we get force. If we differentiate energy, we get force. And when we integrate force, from where to where? Xi to xf. When we integrate force, we get energy minus dv vi to vf. That is equal to what? So so what we cross multiply this implies what? F of x into dx equal to minus dv. Now integrate it on both the sides. Integrate here, apply the limits. Xi to xf, vi to vf. Xi to xf, vi to vf. Now this will become what? Integration of dv will become v, from where? Vi to vf. So that is equal to what? Minus vf minus vi. That will become vi minus vf. Vi minus vf. So integration of xi to xf f of x into dx will be equal to Vi minus V. This is about the potential energy. So we can also write delta V is equal to minus f of x into delta x. Delta I is equal to minus f of x into delta x. Is it clear? Is it clear, girls? See once again, f of x equal to minus dv by dx. Here we are using as a potential energy. Capital V is potential energy. Cross multiply this. Now apply integration on both the sides. After applying integration, dv will become v, vi to vf. Apply upper limit minus lower limit. Then minus of minus will become plus. So delta v is equal to minus f of x into delta x. Is it clear?
Yes, sir.
Yeah. Next is law of conservation of energy. Next concept is law of conservation of energy. What is this? Can anyone say? This is studied in grade 9 again. Law of conservation of energy. Energy is neither created. Energy is neither created
Nor destroyed.
nor destroyed, but can be transformed from one form to another. Energy is neither created nor destroyed, but can be transformed from one form to another. This is law of conservation of energy. Now, conservation of mechanical energy, that we will do the derivation. Copy this.